Go ahead, Mehmet.
Thank you, Dina. Good evening. I'm Mehmet Ansoy, Vice President of Denver Astronomical Society. This evening, we are delighted to have Steve Edberg as our guest speaker. Steve is a retired professional astronomer and an amateur astronomer at home and at his observatory in California. Over almost 38 years at NASA JPL, he worked on Galileo to Jupiter, Cassini to Saturn, the comet rendezvous and asteroid flyby, the Space Interferometer mission, and and other NASA projects. He served as the coordinator for amateur observation for the International Halley Watch. An avid eclipse chaser and expedition organizer, Steve has observed 18 total eclipses from land, sea, and air, 5 annular eclipses, and numerous partial eclipses, and a wide variety of other transitory events involving the sun, the moon, stars, planets, their satellites, asteroids, and meteors. He has also observed other phenomena and NASA experiments in the atmosphere and near Earth space. Steve retired from the Riverside Telescope Makers Conference, Inc. after serving for 22 years as executive director. He has been honored by the International Astronomical Union with the formal naming of the asteroid 1985 QQ as Steve Edberg. And Steve is an avid bicyclist with over 50 years of experience. However, his telescopes still outnumber his bicycles. So, Steve, please proceed with your presentation.
Okay, is everybody hearing me clearly? I hope. Okay. Well, thank you for having me. This was kind of a unusual request. I don't usually talk about myself, but at least it was my understanding that you wanted to hear my stories. At least that's the way I took it. And so I'm going to share a lot of them with you all tonight. And I'll try and leave some time for questions. And I should actually look at my watch and find out when I'm starting. So I am speaking for myself, and so don't go after anybody if you're unhappy with something I say. And I'm now gonna have to figure out how to get this thing to go forward. Oh, there we go. Okay, got it. So this is autobiographical in nature, but it's going to drift into observing and all kinds of things. I'm showing you 2 of my first failures. At age 4.5 or so, I recall that my father took me out into the backyard in West Covina, California, about 20 miles east of downtown Los Angeles, and we were looking for a comet. We didn't see it. It was probably Aron Roland or Merkosha, but I never heard the name, but those are the only bright ones in that time frame that I can identify. And that was followed up a decade or so later with not seeing Comet Ikea Secchi, which is a very frustrating appearance because it was clearly spectacular. So this might not look like a very good start to an astronomical lifetime, but in fact, I went on and had much more success a little later, just only a few years later, getting started. Really, I consider it back as an amateur astronomer, the 1965-66 period, though I had a telescope earlier than that. And really, from 1968, I went to the very first couple of Riverside Telescope Makers conferences, and then as you can see, continued on over many years, most of that 50-year period, in fact, that it was in operation. And I got acquainted with and volunteered at the library of what was then called the Mount Wilson and Palomar Observatories, later named the Hale Observatories, and even later than that, the Carnegie Observatories, which seems to be the name that's probably going to last finally a long, long time. And volunteered at the library. It was good to get acquainted and just be around that place, and getting some of the books that were on the table that were otherwise going away was a nice way to build up my library. That started then a long sequence of through both undergraduate and graduate school years of observatory work, starting at High Altitude Observatory right there in Colorado, and Climax, while the observatory was open for a summer, working on the telescopes. I'm not going to go through these individually. You'll actually see some of them in the slides that I talk about here. But as you can tell, it was a lot of different observatories during my undergraduate and graduate school years, and then a period at San Fernando Observatory, starting my career, moving on to NASA JPL in 1979, starting with work on Galileo, and you can see as well additional work on a variety of projects there. With my retirement from being paid to do things in 2017, but continuing on in 2018 and beyond with astronomy or other teaching. So that's sort of the summary of my career. As you can tell, I've had a number of different titles, or either official or unofficial, that you see down there that are somewhat descriptive of a career that has been very wide open. I should tell you also that I do not have a PhD. It's had both positives and negatives. It's allowed me to be very knowledgeable broadly, though with less depth than being a world expert in a narrow area. It may have impaired my ability to proceed up to something like a project scientist, but it also gave me the opportunity to work across a variety of observatories in solar physics, radio astronomy, and optical astronomy. Even as you'll see a little further along, or look at the list there, you'll see that I worked on interplanetary projects and their instrumentation. And so it's been a very exciting professional career, all the while maintaining my amateur astronomy interests. So with that as introduction, I want to now go on I have these stuck in here in various places, just kind of lessons learned over my 70 years. Some people relish having a variety of activities in their job. I found serving two masters was very difficult, and sometimes I had more than two to do. The other thing that, at least at JPL, was a lot of time those half-time jobs that I might have, or some breakdown of hours, all seem to demand full-time. I'm not sure if that's true at other places, but it sure could be difficult at times at JPL. I also wanted to spend a few minutes, and I hope there are some students listening in and can take this to heart, because this is about getting a career. And if you're interested in really in getting into science or engineering, I think you would find that what I have to say is probably valuable. Some of this is based on my own experience, and the rest is, well, it's really my own experience being on either the application end or being on the old guy end where I have a job already and hiring. If you're interested in getting into astronomy or any science, you can start literally in high school. If astronomy, it's easy because there are astronomy clubs and you can ask speakers questions, you can get acquainted with them, you can correspond with them. Most scientists are willing to share what they know, and in fact, more than willing, they're happy to share what they know and help other students get along, get forward in their areas of interest. And so I encourage that. And there are programs for scientists. NASA specifically even has some for high schoolers, mostly towards high school seniors, but just the same, that's something that you can be looking for. Visit the websites. I've got a list there. I'm not going to read them all off, but there are a lot of places in government and in other institutions where you can find interesting summer jobs, or even sometimes there are part-time jobs during the school year. One of the things I also try and emphasize is that announcements for these kinds of jobs often appear in the autumn, certainly at the beginning of the winter, and they may have very, very early deadlines. I would sometimes see, because I was paying attention, that some programs would start offering or request applications because they were going to be making selections or closing off at least the application as early as January. So you shouldn't dawdle on these sorts of things. And I highly recommend them. JPL, where I spent almost 38 years, has a number of programs, and I think you'd find them very well worth doing. Again, I'm not going to read this to you. You can read it as I go along. I'm just going to use it for prompts. But one of the things anyone should be doing who wants a career is to keep a resume and update it regularly. Initially, it may not go very fast, but at least once a year, you should be able to add things to it. If you're a student, don't self-limit. If you see a program that looks really interesting, even if you don't match the stated requirements, apply anyway. I got into a graduate program when I was in my sophomore year, or end of my sophomore year, in the summer of my sophomore year, at Kitt Peak National Observatory. And just if you work hard at looking for that, you can find them. You have to be enthusiastic, and you'll hear me repeat that later on. If you need letters of recommendation, you should have at least 3 people lined up. Those, in most cases, if you're high school, college, they're most likely going to be teachers, professors, and they should be lined up in advance. And you should give them everything they need to know with plenty of time, and that means 3 to 4 weeks, so that they have time to write the letter for you, and give them some hint on what you're trying to get done and what you'd like them to emphasize, since they know you. I've been giving this kind of advice over several years, and one of the things is you really need to stop and remove anything that might be embarrassing to you or off-putting to a potential employer that you might have on YouTube, Facebook, or whatever social media you're using. Have a professional email address. sweetiepie@emailprovider.com is not going to work. I had to tell that, actually. A young lady was using Love Muffin at whatever, and that just is not professional. Join LinkedIn and keep it updated. That's especially important once you get a little bit of experience. Little bit could still just be a summer job, but that's an important one. I wouldn't expect you to do this for everything, but writing short thank you notes to the people who you talk to in the course of trying to, if you can talk to someone in the course of trying to get a job, is a good idea. They appreciate it and they remember you. Another important thing is learn to write. A lot of people don't use spell check or bother with the grammar checker, and proofreading is very important. Don't burn bridges behind you. And I emphasize again, spell check and grammar check and proofreading are very important. It's so easy to let something go by. So do be careful with that. Now let me talk some about astronomy and where I've been, what I do, and that sort of thing. I'm starting with this because I'm going to be talking about it further on. And it's all will come together. So I'm just going to tell you that this is known as Grandpa. It erupted on the 4th of June, 1946, and it ended up designing a coronagraph. It turns out that the high altitude observatory 3.5-inch coronagraph, which makes artificial eclipses, was designed to allow something like this to be observed again. This actually is one frame of a short video, well, not video, it was a movie at the time, of this erupting prominence, and it completely left the field of view. And Walter Orr Roberts, who was building high altitude observatory at the time, said, well, we're not going to let that get by again. And so that 3.5-inch coronagraph has a much wider field of view. Things like this are rare, but maybe not as rare as you might think. And I will show you further examples as we go along. But the high altitude observatory is where I first got my job. I had made the effort back, this is 1970, to try and find a way to get to see the total solar eclipse in Mexico at the time, when it was crossing the east coast of the US as well, but I was trying to just join an observatory and go there and help out. Well, it didn't work for me to get to go, but I got offered a job to work at High Altitude Observatory in this dome during that summer. And that opened doors for virtually everything else all through my undergraduate and career and beyond. And so what you see here is the 5-inch coronagraph and the 3.5-inch coronagraph, smaller on the left side, and the observatory in a winter scene. But that was very educational and helpful in opening doors everywhere else. One of the takeaways from that is be persistent. If you have a goal, pursue it. And I, at the time, had been trying, as I told you, to find a way to get to that eclipse. Didn't happen for a few years, but I did get this door open to me, and I grabbed it and took it. One of the other things I learned in the process is that you're routinely doing routine work for someone else. You may never receive an acknowledgement from them. That's just the way it is. Sometimes there's too much. I spent a lot of time taking spectra of either the sun's corona or of prominences, and I really never ever heard from the person who had requested all that film at that time. 1971, I actually had a job lined up at the San Fernando Observatory, not too far away from where I live, and it didn't work out because in February of that year, while I was at UC Santa Cruz, the San Fernando earthquake hit the observatory, and very close to the epicenter, in fact. And they needed all the funding that would have otherwise paid for me for the summer to repair the telescope. What was interesting was that the telescope, as you'll find out, I eventually landed there and worked for over a year and a half. But it turned out that there were 3-inch bolts holding the vacuum telescope down on the pier that you see up. If I got there we go. This is the main pier. The telescope is attached to that. You'll see a later picture of this with the observatory open, but these pedals come down, and the telescope sheared off 4 3-inch bolts holding it down and danced on the floor of the observatory building at this level. And you could see it because the walls that separated the outside where the telescope was with the inside where the observing station was actually had dents in it. Really amazing. But that fell through. I ended up working for a company, a Xerox company called Electro-Optical Systems, which was still useful in finding out how optical systems are manufactured in bulk. So takeaway from that, roll with punches. Sometimes outcomes are disappointing, but they're not the end of the world. I spent the spring of 1972 and the summer of 1973 working for Bob Howard at Mount Wilson Observatory. He was the primary solar physicist there, and I got my first publication analyzing data. I was actually, of all things, a computer programmer for that, and used a bunch of subroutines that had been otherwise developed to analyze data coming out, primarily magnetic data from the 150-foot solar tower rather than the 60-foot solar tower. You could guess which one is which. It's not too hard from the scales of those pictures. And we got a publication together out of that. And that was my first paper in the scientific community. After the summer that I spent, after the spring that I spent in 1972 at, I've left a name out, they were Hale observatories for a time as well. I went to Kitt Peak and worked there using primarily the Eastern auxiliary telescope. There are 2 small auxiliary telescopes on the east and west side. We're looking from the west towards the west side. The east side is on the far side. And then up at the top here is an 80-inch mirror that feeds a 60-inch primary telescope. This is just a big flat and the building extends about 150 feet into the tunnel before it gets reflected back to this level for the observing rooms right in this area. This profile has since changed. I had to go chasing down an older picture because there is now a separate observatory and telescope assemblies right in this area in the same in the background. But that worked out very well. The lessons learned in this case is be persistent. If you have a goal, pursue it. And if you don't, figure out what you really want to be doing with your life. It's okay to change over time. Sometimes requirements are bent to fit someone really fit in somebody who's really desirable. So make a good pitch and see what happens. I say that because I ended up as an undergraduate, in having only finished my second year of college, in a graduate program for would-be astronomers at Kitt Peak. The other thing to realize is you should be enthusiastic in your goals. It carries a lot of weight, and if you're enthusiastic, it makes the work involved more fun. After I got my master's from UCLA, I went on to work in solar physics for a year and a half, a little more than that actually, at San Fernando Observatory. And I did some work. Now you can see the observatory. This is in its closed up configuration. If you can see my pointer, I hope so, my mouse arrow. In operations, these 4 pedals came down, and the vacuum telescope up here, I believe it was about a 20-inch aperture, and evacuated in the tube, sent an image down into the observing room down here, and could be analyzed further from then. This was also over here a 5-inch just solar flare telescope. It was not full disc. It was pick a spot that looks interesting and wait and see if something happens. And we were involved in solar flare forecasting, and I participated in, was a part of a paper describing the energy in a solar flare event that we could make from that. After that, I moved on to JPL, and my life broadened considerably. This is the only place I know of where you can bicycle in to work and ride by a Mars rover. And in case you really don't believe me, those are the 6 wheels on that side, and you can see 3 on that side, 3 on this side, but one's lost in the shadow. And that this is one of the models that was used for, in this case, it was the Curiosity rover. So it's a very interesting place to live and work. And a lot of that time it was living. I started my career working on the Galileo orbiter, and in particular, the solid state imaging system. This was the first use of CCDs in a spacecraft. And there was a lot of learning as we went along. I was hired, this particular instrument is right here, and the front end that you see here is actually looking up. This is the stow position, where where it was simply protected from potential damage. Right over here, you can see the visible and infrared mapping spectrometer off to the side. And this is, the whole area is called the scan platform. This is Galileo in the stowed position. I'm spending a little bit of time of it because there's much more story that you will hear as we go along. Here's its antenna. This could have been a spare Voyager antenna, but the science team got greedy. Instead of getting 32,000 bits per second, 32 kilobits per second down, they thought it would be great to get 40 kilobits per second down. And yes, that's true. It would be helpful. But that antenna, which was based on the system that we use, the tracking data relay system that we use for Earth orbiters, didn't end up opening. And that turned into a major problem. My job at the time was to actually write the science requirements documents and procedures for that. And these are the covers of those, of 3 of those documents that I wrote. And that was quite a thing because I'm not an engineer. What I learned there was twofold. One is that get all the help you can from previous documents. So looking at, for example, at the Voyager set of requirements for component calibration and procedures, and then for the whole subsystem altogether, can be very helpful. And going to people who did it in the past is also very helpful. That said, I also learned that people, including managers, don't read things in their draft stage that you think at least they're supposed to. And so if you want to make sure you're on the right path, you have to push them around sometimes to actually get that done. And you also don't be too surprised if it doesn't happen, because I went around for signatures, because this type of document requires half a dozen signatures from people up the chain. And what I thought was finished was apparently nowhere near done. And it was because I hadn't gotten enough indication of what was needed. So just need to be careful. In the process, though, of working at JPL, I learned that there was going to be the International Halley Watch, and they wanted to have someone to coordinate amateur observations, and that expanded into general outreach on comets at first, and especially Halley later on. And the result was a chance to write books and collect data. And these are the books that resulted from amateur data only for Comet Giacobini-Zinner, which was a kind of a practice comet. We actually did have a much smaller publication for an earlier comet that was sort of a proof of concept. And of course, the archive for the amateur observations for the International Halley Watch of Halley's Comet itself, and that was the size of a phone book. All of those observations are also recorded on a set of about 30, well, compact discs, old technology now, but they're included with the 30 compact discs that describe all of the records of the International Halley Watch. This was a very enjoyable part of my career. So one of the lessons learned here that I learned also in the course of remaining an amateur astronomer was to push your telescope and yourself to your limits. And the reason I say that is that when I went to look for Halley's Comet 1 year after its close, well, actually it was about a year after its closest approach to Earth and about 14 months after it was at its closest to the sun, perihelion, and found it, I thought. I was using a 12-inch f4 observatory telescope for Polaris Observatory Association up in the mountains north of Los Angeles, extension of the San Gabriels near the Los Padres National Forest. And I finally got on the field, and I'm looking at it and trying high magnification to try and see where can I see a blob. And the trouble was, all I saw were blobs everywhere in the whole field of view. I switched eyepieces to one that was actually a little lower magnification, but much higher quality. And I didn't realize how high the quality was. And that switch then presented me with one little blob that was the comet, and everything else were pinpoint stars. The lesson being that the right eyepiece can really do a job, and ones that are not as well made are not necessarily going to be able to show you when you push your telescope to the limits. It has, in a sense, made it very much harder for me to buy eyepieces now, because I kind of insist on checking them before I putting them to use before I'll buy one, because it's just too hard to know which are good. There's a lot of nice eyepieces out there, but you really need to know what you're talking about if you want to get the most of out of the telescope. As the Halley Watch was winding down, I was still doing a lot of preparing the data that appeared in those books. I had to take a second job, and that was to end up being an investigation scientist for the visible and infrared mapping spectrometer and the thermal infrared radiometer experiment for the Comet Rendezvous and Asteroid Flyby mission, CRAF, which was part of what was called Mariner Mark II. The updates, in a way, to in some cases, orbiters that would follow on for what, well, in essence, the Voyagers had been doing. And down below there, you see CRAF on the left and Cassini-Huygens on the right. These are very early drawings of all of them. The color one in the top left is Kraft with its comet probe, and actually a later derivation even than the one. No, actually, I guess I might say that that's earlier, now that I think about it, of the one down here. So spacecraft go through a lot of design and redesign over time, and this just gives you an example of what's going on. One of the things that I learned is that sadly Kraft was eventually was canceled, and that was very, very disappointing. I eventually joined the Cassini mission, but the Cassini spacecraft did not look like the one that was in the lower right of that screen. I also ended up joining Galileo, and this was what the path it was intended and did take to get through the solar system after launch. The launch was delayed by the Challenger disaster when the Space Shuttle Challenger was destroyed during its launch sequence, in fact, that delayed Galileo's launch by 3 years, 3.5 years, really. And so this is the path that took Galileo to Jupiter. You'll notice it was called a VEGA, V-E-E-G-A path, or Venus, Earth, Gravity Assist. It also conveniently went by the asteroid Gaspra and another asteroid a couple of years later, Ida, on its way. And it was not an easy, smooth mission, unfortunately. A lot happened. It was very successful. But as you can see, here's Gaspra, here's Ida, and here is, at the same time, Comet Shoemaker-Levy, thank you, David 9, the scars from the impact of that on Jupiter, all of which were observed by Galileo in a configuration in which the main antenna up here only partially opened. A lot of good science ended up coming from it, but boy, it was a real challenge to make all of this work. And I'm going to explain a little bit more as we go down. I'm also going to show you and ask, though I don't think anybody will be out there to answer, so I will, but this might look like a comet. And in fact, when I've got a live in-person audience, I ask, well, what are we looking at? And a lot of people will say, well, that's a comet. And I'm going to tell you, no, it's not. This is an ultraviolet image made with a University of Colorado instrument, the ultraviolet spectrograph Galileo was carrying. This is Earth, this is the moon, and this comet is the extended atmosphere of Earth caused by the solar wind. But it also then begs the question, I like to ask this sometimes, is this a comet? And well, no, it's not, but what makes a comet different from this? And I'm going to leave that for you to ponder. I followed on with the cancellation of Kraft, Rendezvous asteroid flyby, with the continuation of the Cassini. And here you can see the configuration of Cassini as flown. You might remember it had a couple of wings sticking out, not really wings, but support structures that had a high precision scan platform on it. And in the course of the period when Mariner Mark II, the Kraft and Cassini missions were threatened with complete cancellation, redesign was made to provide this spacecraft, which has all the instruments. These are the optical instruments mounted solid on the whole spacecraft. So if you're going to look somewhere, you turn the whole spacecraft to do it. That sometimes doesn't work if you want to have two things aimed at the two very different things aimed at the same time. For instance, this is the dust detector on this spacecraft, and you might prefer to be having it looking at say the ring system at the same time that you're actually imaging the ring system, and you cannot do that on this type of spacecraft. Still, it got to fly, and this is just an example of some of the planning software that we had for figuring out what to observe. And so I'll just show this to you. And this is the narrow angle field of view. This was essentially a 2000 millimeter focal length lens, that or mirror lens, better built than a C8, but it's the same general idea. And a matching wide angle, if you're a photographer, you wouldn't consider that wide angle. This is a 200 millimeter focal length lens, but this is the field of view of it. And the planning software here shows the F-ring of Saturn with a high resolution image being planned to kind of get the image, the end of the ring going right through there, and a wide angle image here and what it should look like. Well, if you compare then what the wide angle view looks with the matching actual image, looks pretty good. You can see that there is a little bit of difference here. This was actually designed to go right through the center of the F-ring, was to go right through the center of the narrow angle picture. Nope, came out off. And that's one of those things where there can be a little bit off. As perfectionist as the spacecraft assemblers are in trying to make things exactly collimated like a pair of binoculars, they can't be perfect. And this is a case where you just have to plan around that sort of thing. The other thing that I was involved with the composite infrared spectrometer. Maybe I ought to see if I can go back up and just point it out to you. And that's on this end. This section here these are just covers for the thermal radiators on all of the instruments on the spacecraft. These are the two cameras, and in here is the ultraviolet spectrograph from the University of Colorado. Here is the VIMS instrument, visible infrared mapping spectrometer, and they are mounted so that they are actually looking at the wall of the spacecraft assembly facility here in this section. One of the other things that I was doing at the time was, besides assisting with selecting what the prime mission would look like, and here you see not quite the final version. I'll have a story for that in a minute. But this is basically the way we best came up with for getting the data that all of the instruments, 18 instruments, 12 different teams, science teams, to collect data on Saturn so that we would better understand that. And so it was divided. You could see where we could get radio signals through the ring occultations, or even measure sunlight going through the rings. We could look at the rings of magnetosphere and other portions of the orbit, and also set up the dropping of the Huygens probe into the atmosphere of Titan. One of the things I was involved with was helping with the planning, and the science team decided that they wanted to plan all 4 years of the primary mission in advance of arrival at Saturn. And so that's a lot of work to do, though we had enough transit time to do all that. And so we eventually developed software that presented this. Now, I know this is just like colors to you and may not be legible, and I understand that, and you don't really have to read it, though I tried to make some of it more visible, and you can actually see down here, Sears, ISS, UVIS, and VIMS are the four optical instruments that are aboard. And this is the rings sets of measurements that are proposed by the science teams. Here are atmospheric observations proposed by the same science teams. Here are the surfaces science teams that might be proposing observations of the satellites. The radar is here. We're passing by Titan. These are the fields and particles instruments, we called them. And then we did have to pay attention to what maneuvers the spacecraft might have to do. And there were 3 engine burns planned for every one of those pedals of the orbital path for the spacecraft. And there are engineering things that had to do. And so we had to avoid constraints, a lot of things that were involved. The funny thing about this is that this, oh, and just so you know, up here, DSN, that's the Deep Space Network. That's going to be who can track us when. And playbacks in particular are here, where you can see, if you read them carefully, it says Goldstone and Goldstone, Goldstone. So all of this period was going to be Goldstone instead of the Madrid or Tidbinbilla, Australia, or Canberra was the actual station name. So, and this is between, I just happened to pick between orbit 3 and orbit 4, the switch occurring at apoapsis, the most distant part of the orbit of the spacecraft. This was a royal headache because we had 55 orbits to arrange, and the bulk of the first 4 years of the mission. And just to show you an example, if you were to look at the imaging science team, ISS, here, the imaging solid state imager, ISS. It should actually be SSI. I don't know why I put it in that way. You can see that sometimes ISS measurements, and I don't have a particular one to point out, they actually were competing with each other. So surfaces might be wanting to do something the same time the atmosphere folks wanted to look at clouds, at the same time the ring people might be looking at rings. So the imaging team at this stage hadn't even decided who was going to get priority. It took about a year of the kindergartner who were on the science team fighting about this to actually, for me in this case, to finally sit down, look at what everything was going on, and come back to and say, okay, this is what I recommend we do, and then let them have at it. And the good news was that actually got them starting to work together. And so it was very much a diplomatic process, and I was never sure who was going to jump on me for doing something wrong, but it worked out. And whereas all the organizations, rings, atmospheres, surfaces, and fields and particles, all, and Titan all by itself, there were 5 of them, whereas we all had the same 4 years or so to actually do this planning. My group, which also had the bulk of the actual time, because we were working on all of the outer portions outside of Titan's orbit, all of the outer portions of these, we finished ahead of everyone else, and it was successful, and I'm very proud of that. Now, Cassini used a Venus-Earth-Jupiter gravity assist. And even though I was deeply involved in it, I'm not going to, and don't have time to talk about what was going on with the launch, which anti-nuclear people did not like having radioisotope thermoelectric generators launched on spacecraft, and especially having one make a flyby. There were court proceedings and all of that. I'm not going to talk about the details of that. But what I do want to do is show you what happened. And if there's time, I want to return at the end maybe to, somebody should ask me about Galileo's problems. So this is what the trajectory looked like. The spacecraft was going along and was going to be making these close flybys, and yeah, some of the things got left out. I'm sorry about that. Checking my notes here. And we took some time to do a variety of things, but it was literally pulling teeth. Well, not literally, obviously, but it was like pulling teeth. The spacecraft had been built to only have keep alive software. In other words, the flight software was what would allow it to go through the inner solar system, get through the gravity assists, and then hopefully not have any, and then over time, which was going to be about 4 years, it would get the flight software necessary to do other things. And doing other things meant, like, well, it would be nice, maybe we could try and observe Jupiter, and maybe we could try and observe an asteroid or something like that on the way to Jupiter, and do things that the Earth swing by. It was difficult because of the concerns about doing anything that might bring the nuclear generators on the spacecraft back into Earth's atmosphere. It turns out we missed the target point by less than 20 miles in space. So that didn't happen or come close. But there were a couple of mishaps. And on the second flyby of Earth, or I'm sorry, on the flyby of Earth, just afterwards, by a couple of weeks, there was a switch that was made from using, there were two star cameras on board for keeping the spacecraft oriented. And in the course of, it was good to exercise them both. And the way that those cameras worked was to actually was to have them take a picture, 30 seconds later, take another picture, compare the two pictures. As long as the spacecraft had the same stars in the same field of view, everything was copacetic. It's great, it's working. Well, after the switch from A to B was made, there was a little something off. And the spacecraft, there's software on board for this sort of thing. And it said, okay, I'll take another picture and then see what happens. Well, the third picture was off as well. And so the spacecraft is designed to say, okay, I got a problem here. I'm going to turn towards the sun, go back to my low gain antenna, and I'm going to call for help. And it did that. Well, this is one of those lessons learned. What had happened was that as closely as the assemblers of the spacecraft had tried to make it, the two star field cameras were not precisely collimated. And so the spacecraft went into what is called safing, and that ended up causing the spacecraft to, phone home and say, what's going on? They looked at it, they said, okay, that's what happened. Lesson learned. From now on, we have to make sure that we say, after a switch from A to B or B to A, you wait 2 or 3 frames, not just the usual 2, to confirm that there isn't something wrong. And so that got solved. The reason I tell you this is to emphasize that spaceflight is a human endeavor and people make mistakes. And that was just one that sneaked up and bit us. Another one was, at the time, on the way flying out between the orbit of Mars and Jupiter, there was going to be an asteroid at about 1 million kilometers, about 600,000 miles away from the spacecraft. That was the closest one that we came to. So if you think that they're all close together, the way Star Wars asteroid belts are, you're mistaken. But the team made the imaging team said, really, we should just take advantage of this. We can just do a little bit of photometry on it. It was a good thing they did, because it turned out that the pictures were not centered anywhere near where they were supposed to be. They barely got the asteroid into the narrow field cameras. I'm not saying this right. Sorry. The narrow field of view of the primary, the 2000 millimeter camera. And it was just at the edge, in fact. And they asked, what was the problem with this? Well, it was a good thing to found out, because it seemed as though two of the flight team sub-teams were using different coordinate systems for the pointing of the camera. And they weren't the same, and therefore the camera didn't get pointed correctly. So again, a lesson learned. The most potentially interesting and funny one in a way, and happily with enough time to save things, was again on the way after the Earth flyby, the swing by they called it in this map. And it was to test the Huygens probe's receiver on the orbiter spacecraft. The Huygens probe was to go into the atmosphere of Titan, send back data, and be relayed through the main antenna back to Earth. And so they did that. And it's a very elaborate test. They actually tried to show, they tried to change the frequency of what was a fake Huygens probe on Earth to match what the receiver on Cassini, the orbiter, was going to be seeing as it went by. And they found big problems. What had happened? Well, one end of the Italian factory building the receiver didn't talk to the other end of the Italian factory building some other part of the receiver. And it turned out that they had changed the design, and the Doppler shifting that was supposed to be accounted for was not going to be accounted for. So that elaborate flower of orbital paths had to be changed. It went from, instead of 1, 2, 3, 4 to 75, it went from 0 to A, B, C, 4, 5, 6, 7, 8 out to 75. That was because they had to change what was going to be a close 900 kilometer distance flyby of Titan when the probe was going to be going by, out to a 50,000 mile flyby, so that the Doppler effect would not affect those signals as much. Again, this is a human endeavor and people make mistakes. Further along in my career, I got to join as, well, a couple of different titles, depending on who you ask and what I was doing. But the Space Interferometry mission. And one of the things that I learned as far back as, well, in the the early 1980s, is when a spacecraft or project starts having to change its spacecraft name, it probably has problems. And that is what turned out to happen with SIM. That's what happened with, well, the name changes didn't happen with Craft, it was just canceled. SIM fought a harder battle, having first been suggested in what was called the Decadal Survey of Astronomy and Astrophysics in 1980, endorsed in 1990, endorsed again, and in the process of being started in 2000, and then it got a footnote, couple of paragraphs long maybe, in the 2010 Decadal Survey. Very frustrating. It did get canceled. This was a mission that was going to measure star positions. Now, when I got aboard, I was thinking this has got to be really, really boring. Who cares about astrometry? And as I learned more, I discovered that there's a lot of interesting things that you can do once you can do astrometry. And this kind of talks about that. This spacecraft would have been able to measure as closely as 1 micro arc second, 1 millionth of a second of arc. Just for scale, the moon in the sky is about 3,200 seconds of arc in diameter. The satellites of Jupiter, when you can see them on those nights of really good seeing, range to 1.5 to 2.5 arc seconds in diameter. So we're looking down at 1 millionth of it. That's the thickness of a nickel. Think of Buzz Aldrin holding a nickel edge on, and that thickness of a nickel would be seen from the surface of the Earth to the surface of the moon, could be measured. It's a tiny, tiny amount, but it allowed us to actually be able to look for Earth-like planets, Earth's mass planets, orbiting stars as far as 10 parsecs away. It was going to be much more effective than Hipparcos was in studying with distances out to 2,500, 2,500 parsecs, about 7,500, more than that, 8,500 light years, down to 1%, and even to the edge of the Milky Way galaxy to 10%. We would have been able to measure proper motion of stars against the sky in the Andromeda galaxy, just as an example. Fabulous mission, got canceled. I rounded out my career working on Earth science. So I got to cover overall, in one way or another, missions that we're going to look at the sun. Let's see, Earth, Mars, Jupiter, Saturn, Pluto. And so it was quite a career. The soil moisture active passive looks for, and is still in operation as far as I know, measuring soil moisture, how dry are things. It was able to look at just how wet the ground is, or how snow covered it is all around the world, at least high up to 57 north and south. GRACE, the Gravity Recovery and Climate Experiment, and I have a little thing to show you here, actually measures gravity. And as it orbits Earth in a polar orbit, when it goes across a continent, the lead spacecraft, which is a couple 100 kilometers, 120 miles or so in the lead, actually gets pulled faster than the trailing spacecraft until it passes over the continent, and then it slows down again, and the other one is being pulled forward. And by measuring these, you can actually figure out how much gravity is pulling on them underneath over large continents, well, smaller than continental, maybe tens of miles areas. And we can actually see, for example, in California, the water that is diminishing under the Central Valley because it's being pumped out. Same is true in India and in the Middle East. We could see the water that comes and goes with the rainy season in the Amazon. So a lot of interesting stuff. And there that is again. I'm going to see if I can get a page down here. I'll just let that roll one more time. There we go. All right. So how am I doing on time, powers that be? I didn't look at my watch. And we have enough time to keep going?
We should probably start wrapping it up and get ready to take questions. I saw that we had a few in the chat.
Okay, well, this was a spot that I kind of planned that might be the case. So why don't we just go on with that? Let me, I'm going to jump way ahead and kind of close out sort of with some takeaways that I want to share with you
Okay.
from this.
Sure.
And you can just read them, and let's just start with questions.
Sounds good.
Well,
I
Tina,
like that.
you want to lead this? I have a dog barking here in the background.
That's fine, Mehmet. I'll take care of it. I like this dadphorisms.
That was her invention, Shauna's invention. I did too. That's why I used it.
Is she the one that is the mother of your new grandson?
No, she is not. Our elder son
Ah,
is the
okay.
father.
Okay. Oh, I would agree with all of this. Yes. Excellent. Well, the first question that I came across, actually, I only see a few questions, and they're from Joe Pineda. Joe, would you like to unmute and ask your question, discuss the question you have?
Sure. Thank you, Stefan. This was Mr. Edberg. This was very good.
Steve.
If you go back to your slide 10, I have a question about the foreground observatory.
Okay, hang on a second. Let me see. You're going to get to see maybe some of my, there we go. But this way I can move around and really see what you're asking for, if that's all right.
Yeah.
Let me go up to full size on this and raise this. Whoops, a little too big. There we go. And slide 10.
Yeah. So
there we go.
So the foreground observatory, the one where the scope shoot off the 3-inch bolts, why is the observatory, why does it look like that?
It turns out that the ground effects of heating can be mitigated some by getting above the most immediate heating. And so looking here, let's see, I should have another, yeah, I will jump ahead to this one if I may. I know it's a little bit smaller, but you can see how the telescope opens up. This is the telescope pointed at the sun now. Mm-hmm. If you can see my pointer, and getting that above that low surface layer does reduce seeing. That's exactly why this is a solar flare telescope, and it's also elevated for just that reason, to make it available. This is an earlier picture. You can see they built a structure around it so the observer could actually get up there and change film more conveniently than otherwise here. But this is the way this one operates. Was that clear enough?
Yeah. So basically, you have thermal effects from the ground impact.
Yes.
Oh.
Yes, and in fact, you can see here that this is a later picture, significantly later picture, because this is one of the reservoirs that was built on a peninsula in this reservoir at the north end of San Fernando Valley. And the idea was to quiet the air by having this big body of water. Oh. And I can personally vouch for the fact that I saw some pretty spectacular steady seeing there, but other times not always. But it helped to have the telescope elevated and it helped to have a vacuum in the actual tube of the telescope, which is pointed at the sun up here, and you can't see all of it, of course, but and so that combination of things made for very much steadier seeing.
Interesting.
I got
Thank
some
you.
really good lunar pictures as well from up there.
Thank you very much.
Sure.
I can
I have a,
imagine.
I have a question. Steve, this was an excellent presentation. Thank you very much. My question actually is related to this nuclear-powered mission that you said created problems for the, I think, which mission was that? Is that the Cassini mission, I guess you mentioned? What is the latest view of NASA on nuclear-powered missions?
Oh, okay. Let me give a little bit of background, if I may. Every mission that carries nuclear material has to go through an environmental impact process. It just got frenzied for Cassini, but it happened with Galileo, and it has happened earlier. And I imagine there, at least the process had to go through for even the Mars rovers that had just even the simplest one that was carrying plutonium, just heaters on it. Could you, I wanted to give that introduction, but now I've forgotten exactly what you asked.
What I think my point is more related to nuclear-powered propulsion system focused. It's not that whether you carry any nuclear material or not, but whether the propulsion systems use nuclear material or not, and whether missions are going to use that going forward. I assume they will, but what is the latest on that?
Well, I'm going to say that I have not kept up with that. I can tell you I have a little bit of personal history with it because my father was an engineer at Aerojet, and he worked on the SNAP system, which was a space nuclear, I can't remember what all, propulsion. Can't remember exactly what the SNAP stood for. There was in the 80s a discussion of actually going to nuclear propulsion for interplanetary spacecraft, which I was just imagining what the environmental impact issues would be with that. It was later canceled. I was also imagining more what you could do with a really high-powered radar, for instance, with essentially no limits on the power compared to what you have with the systems that Cassini was carrying. And so right now there's, and I again, I'm going to tell you, I haven't looked recently at this. So, and I apologize for not knowing more, but
that's all right. That's all right. You mentioned the trouble related to the missions with regard to nuclear material. That's why I thought this issue might have been resolved by now. But anyway,
well,
thank you.
To some degree, it is there. Right now, for example, Juno around Jupiter is solar powered, and at the time, Galileo, which was also orbiting Jupiter, was not. So NASA is hearing that. On the other hand, and no nuclear propulsion is really being proposed that I'm aware of right now.
Okay.
It's just environmental stuff is really difficult, and we really had a fight on our hands in Florida back for the launch of Cassini.
Okay. Well, thank you very much. Are there any other questions? Let me see whether there is. Yeah, Jack is saying it's great presentation, brings back memories of several of these missions, and I totally agree. Great to see you as well, he says. And
Hey, Jack.
yeah, any other questions from the members?
I don't have a question, but I just wanted to say again, Steve, thank you very much for your donation of the 2 telescopes. I'll be meeting with people from Douglas County Open Space again next week. We're partnering also with the Colorado Springs Astronomical Society and working on bringing in more partners. It looks like the funding is coming through this year for the observatory at Sandstone Ranch. So we hope to be installing your telescopes there sometime around the end of this year or early next year. And I can't wait to be sending you pictures of them up and running down there.
Very glad to hear that.
There is a question about your cycling.
Oh, okay.
Did you ever ride your bicycle down the Angeles Crest Highway from Mount Wilson?
Yes, I have.
Roger Wendell is asking.
That's actually it. Mount Wilson has a pretty narrow road, so you have to be pretty careful coming down it. There are also, for the mountain bikers out there, you can take trails, and I've been down that too. But you want to, as I say, you need to be careful. The trails are actually mostly dirt road or wide enough that it's not real extreme bicycling, but I have done that as well once.
How many bicycles do you have?
3, but I'd rather you not mention that to my wife.
Okay. So
I
you
have
must
more
have more telescopes than that. Okay.
Yeah, and she's more irritated with those.
With the telescopes or bicycles?
The telescopes.
Well, we did help you out with that.
Yes, you did. You did.
Well, thank you very much, Steve. We very much appreciated your presentation tonight, and maybe we'll ask you to give a more topical presentation in the future. We would welcome you coming back for another presentation down the road.
Sure, that'd be fine.
That would be lovely. Thank you.
Thank you very much.
Thank you.
Okay, very good.